today we are going to discuss about angular momentum. Yesterday what we talked about angular velocity or angular speed and angular acceleration, and we derived for total acceleration of a particle, that is equal to tangential acceleration plus radial acceleration. Okay, so this alpha is angular acceleration and this is linear acceleration. Total acceleration is linear acceleration. So we are going to discuss how this is related. So if radial acceleration is absent, then in that case only A is equal to R alpha. We have already discussed this. Here we have discussed A tangential is equal to R alpha or V is equal to R omega, right? Similarly, we are going to discuss about the angular momentum of a particle or a system of particles. So I will type here angular momentum, right? So we write this as a symbol L. This is also vector, so we write the bar over this vector, right? So this is L bar. So in previous chapters we have seen this L bar is nothing but R bar cross P bar, correct? R bar cross P bar is our angular momentum vector. So if we take the magnitude, what will be the magnitude of this? The L is equal to R into P. We consider that these two vectors R and P are perpendicular to each other. So sin theta, what is magnitude of this? It is R P, R P and sin theta, correct? So when the angle between R and P is equal to 90 degree, so in that case what will happen? Sin theta will become 1. So my maximum magnitude will be equal to R into P. So what is P? This is linear momentum and we write this as M into V. So what will happen to this angular momentum definition or magnitude? R M V. Okay. So as this is magnitude, we can change the order, right? As this is constants, or we can say this is magnitude of the vector, so we can change the order of this because this is just like constants. So I can write the magnitude is equal to M V R. Okay, so magnitude of the angular momentum is equal to mvr. But when we discuss the rotational motion or any angular motion like rotational motion or circular motion, what we have, we can only use the angular terms, right, which we have discussed earlier. We can either use angular displacement, that is theta, angular velocity or angular speed omega, then angular acceleration. We do not use the v. So what we will do, we will use the definition of v or the relation between v and omega, which we discussed in the last lecture. We will use this definition and we will find out the magnitude for L. So v is equal to r omega. Therefore what I will get, m into v is equal to what? R omega and into this r. So there are two r, so r into r will be r square. So the magnitude of angular momentum is equal to m omega r square. Okay, so note this down. This is the magnitude of angular momentum. So we will, most of the time in rotational case, we will use this definition, m omega r square. In other cases, if we are studying some straight line motion or translational motion, then in that case we can use mvr. Okay, but in rotational motion, what we will use? We will use m omega r square. Now I can write this differently for system of particles. So we have discussed if there is a system, then what we have to do? We have to sum all the quantities for all particles. Let's say ith particle. So the summation is going from I is equal to 1 to n. So if there are n number of particles, then we have to add all n quantities. Let's say for Li, this is angular momentum of ith particle. So there can be n number of particles in the system, so we have to add all the angular momentum. So this will be our total angular momentum of the system, right? So this is L. Now for each particle mass we will write as Mi. Okay, so Mi okay, this is summation from I is equal to 1 to n. I is equal to 1 to n. This is I. So what will be the case? Then R is also different. Okay, let's take one example. Let's take this is any random body, any random shape. So if there is particle here, then the distance will be this Ri. Okay. If the another particle is here, the distance will be different. Here the distance will be different. So it can have varying distance. So we have to add all the Ri. So Ri must be under the summation sign, and it's square. You can see here it is squared. So Mi Ri squared and omega. Now this omega is same for all the particles, because this system of particle or this body is rotating as whole. If this particle has omega, its angular speed, then other particle will also have angular speed omega, right? So omega is not going to change. Therefore what we can do, we can take this omega outside the bracket. Okay, so this is omega. So we are considering that omega is constant for all the particles. Okay, so this, do you remember what quantity is this in the angular motion or rotational motion? Do you remember? In offline lecture we have written the formula. Correct, moment of inertia, I. So we can write this as equal to I. So I is the moment of inertia of this body, and omega is angular speed or angular velocity of this body. So how we can write this? For system of particles, L is equal to I omega. Okay, so if single particle is there, then angular momentum is equal to m omega r square. You can use this definition. If there is a system of particle, then what we will do? We find out the moment of inertia of that system of particles or of that body, and then we multiply that with the angular speed. So this is our angular momentum of a system of particles. This is angular momentum of a single particle. Okay. Now in translation motion we have kinetic energy. I will write the symbol T for kinetic energy. This is equal to half mv square or mv square by 2. Okay, again we can do one thing, we can multiply and divide by m on this side. So this will become m square v square m square v square upon 2m, right? So what I have done, I have multiplied m on denominator and numerator. So m becomes m square and here 2 becomes 2m. So if you have to cancel one m, then again this will reduce to mv square by 2. So what is mv? Mv is our momentum p. So I can write this as a p square upon 2m. Okay, so this is what? This is translational kinetic energy. So mv square by 2 or p square by 2m is translational kinetic energy. Now what if I have to find out the rotational kinetic energy, right? So as we have discussed earlier, there are some analogous functions like force is replaced by torque or momentum is replaced by angular momentum. So similarly, this kinetic energy, translational kinetic energy, or this is kinetic energy if the particle or the system of particle is moving in one dimension or one direction. But if the particle or the system of particle is rotating, then it will have rotational kinetic energy. I will again write T R. Let's say T R for rotational kinetic energy. So can you tell me from this what will be the rotational kinetic energy? What is analogous in rotation for P?
L.
L. So L is angular momentum. So instead of P, I will write L square. P square जाके क्या आला? L square आला. Divided by 2 is constant, so it will be as it is. And then analogous to M, what will be the I? That is moment of inertia. Correct. Very good. So this is our definition for rotational kinetic energy. Okay, L square upon 2I, where I is moment of inertia and L is angular momentum of the system. So this can be for a system. Okay, so when suppose there is only one particle, I will take one particle, very small particle. So if this particle is rotating about itself, we cannot notice that. Okay, आपल्याला कळणार नाही एकच पार्टिकल जर आहे तो गोल फिरला तर, ठीक आहे. बट वेन द सिस्टम ऑफ पार्टिकल इज देअर, वी कॅन फाइंड आउट ओके दिस इज rotated and this has become this. If this system is there and it is rotated, then we can notice the change. Okay, so this particle are at a very short distance, these are having very large distance, I mean they are separated with large distance, so they are reversed. This side has become to right hand side and right hand side become left hand side. So you can see there is some change if the system of particle is there. So therefore when we talk about rotational motion, we generally discuss about the system of particles or one single body. We cannot discuss for a single particle. If single particle is rotated, we cannot know how it is rotated. Okay, therefore rotational kinetic energy is this L square upon 2I. I is the moment of inertia. Okay, now what will be the torque? You know the relation, torque is equal to R bar cross F bar, right? This is one definition which we use in earlier topics, but now we can use one more definition. This is also equal to dl by dt. Do you remember this definition? Change in angular momentum per unit time. This is what? Torque. So we can use this definition. So what is L? We just discussed in the last point. You can see here m omega r square. For there is, if there is single particle, then this is m omega r square, or if that is system of particle, then we use I omega. So we will generally use I omega because we know we discuss the rotational motion of the system of particles, right? Therefore what we will do, instead of this L, we use I into omega. Okay, so d by dt of I omega. So I, which is the moment of inertia of the system, and it depends on the axis of rotation. Okay, suppose okay, this is a body and this is a axis of rotation. So this body is rotating around this axis. Okay, so the particles on this axis are not moving, but all other particles, let's say this particle, it is moving in circular motion along this axis. Okay, suppose this particle, so this particle is also moving in circular path along this axis. So whenever we talk about the I, this is moment of inertia, we talk about m r I square. Okay, I am not writing I, m I r I square. So from this axis, r is not going to change because they are following the circular path. So for a circle, r is not going to change, and the mass of the particle is also not going to change. Therefore This I, moment of inertia, is not going to change with time. So we can treat this as a constant and we can take this outside the derivative. So this is equal to I into d omega by dt. So, or we can write omega dot. So what is the derivative of omega with respect to time?
alpha,
Alpha. So that is angular acceleration, right? So you can write this I alpha. So this is your definition for torque. Okay. So note down. We learned today two definitions, three definitions actually. First one is for angular momentum of the particle m omega r square. Then for system of particle it is I omega, where I is summation of mi ri square, okay, over I is equal to 1 to n. Then we discussed what is the translational and rotational kinetic energy. We just compared these two things and we have written this formula. And then this is torque. So generally we can use this definition or this definition. But in this definition, what is the problem? We have to solve the cross product and we have to put the value of f. Instead, what we have done, we have just found value of L and we have taken the derivative, right? So we substituted this value. I is anyway constant because when the axis is fixed, then the moment of inertia is also fixed. If I change the axis, okay, I will draw with different color. So if I change the axis, then the I can change. But for a single rotation motion, I is not going to change because axis is not going to change. So for this axis, there might be some I2, different moment of inertia. Okay. So if there is another axis, let's say this axis. So for this, there might be some I3 will be there. Okay. But as long as the axis is fixed, this moment of inertia is not going to change. For this axis, the body can rotate with any angle. The I3 is not going to change along this axis. Okay. So this I is taken outside of the derivative and d omega by dt is called as a or it is angular acceleration. Okay. Or from this definition we have already discussed in third chapter. What is r cross f? What will be the magnitude of torque? Just like we discussed the magnitude of angular momentum. This is rf sin theta, right? We discussed this in detail. So when torque can be 0, when r is 0 or f is 0 or the angle is 0, right? We have discussed this. So when angle is 0, sin theta becomes 0. And this is maximum if sin 90. Theta is 90, then sin theta is equal to 1. So in that case, r cross f is maximum. So we have discussed the work done in translation motion. What is work done? W is equal to integration over, or let's forget about integration. What we do? Force into displacement, right? Force into displacement. Let's say dx, or sometimes we write ds. So this is dw. So we have to integrate this over the range, whatever the distance is from x1 to x2, let's say. So if the particle is moving from x1 to x2 and the force applied is F, then we get the work done is equal to this. Now for rotational motion also we have work done. Okay. So what will be the work done for that? I will write WR. So this is work done for rotational motion. This is for translation motion. So again, just use analogy. F च्या जागी काय येणार? फोर्स च्या जागी काय येणार? टॉर्क येणार.
torque,
हां, F च्या जागी येणार आपला टॉर्क. And what will be at this? Instead of linear displacement, we will have angular displacement. D theta. Okay. So because you're right, theta is there, but because this is integration, we have to write in this form, d theta, dx, dy, dt, right? Therefore, we write here d theta, and instead of x1 to x2, we will have the integration from theta 1 to theta 2. So you can just use analogy to to derive the formulas, we don't need to write all the formulas, we don't need to derive everything. Okay. So if the system is moving in straight line, like okay, let's say earth is revolving around the sun as well as it is rotating around itself, so it will have translational kinetic energy plus rotational kinetic energy, right? So we will derive that part also. We have already written the kinetic energy, na? Yes, L square upon 2I. Okay. Or if you know, if you can put the value of L, what will be the value of TR, or kinetic energy of rotation? Or you can, instead of this, use this definition, use analogy. Instead of M, what I can write? I can write I, right? Instead of V, I can write omega. So omega square divided by 2, right? So either you can use this analogy, or we have value of L. L is what? I omega. Like P is equal to mv, we have L is equal to I omega. So this is similarity. So you can use either this definition for translational kinetic energy. So we will use this definition. So total kinetic energy is equal to, first, translational kinetic energy, let's write it ET, plus rotational kinetic energy, that is ER. Okay. So in general, what we write for ET, this translation motion, mv square by 2, mv square by 2. And for kinetic energy, just we discussed in rotation, it is I omega square by 2. Or we can also use L square by 2I. Any definition we can use depending on the case. So if we have given L, then you can use L square by 2I. If you have given omega, then you can use I omega square by 2. Right? So what if it has both motions? We can add this together. And we can write for omega, omega is equal to V upon R. Right? And I is equal to M R I. Okay, but this is summation, right? Summation M I R I squared. So to ignore this summation, we define one new quantity, and that quantity is called as a radius of gyration. So in that form we write this is equal to M. So this is now total mass into K square, capital K square. This K is called as a radius of gyration. So for this, how can I write the equation in case of I and M? This is equal to under root of I upon M. I just rearrange this equation. So this is called as radius of gyration. Okay, I will type this. This is radius of gyration. Okay, this is radius of gyration. K is equal to under root I, where I is the moment of inertia of the system and M is total mass of the system. Okay, so we will use these two definitions. Omega is equal to V upon R and I is equal to M K square. So what will be the case? Oh, sorry. This is equal to M V square. So this is M. This M is total mass, V is velocity plus by 2 plus, instead of I will write M K square. In place of omega, I will write V square upon R square, because omega is V upon R, its square will be V square upon R square. So I will write R square below R square and this 2 as it is. Right. So now from this equation I can take mv square by 2 common. So this is equal to mv square by 2. So I have taken this common, and what will be inside the bracket? Here only 1 is remaining because all is taken outside or common. So 1 plus, here what is remaining? K square upon r square. You can use either capital R or small r. Okay. So this is your total energy, total kinetic energy. When the system or when the body is moving forward in translation motion, as well as it is rotating around itself along certain axis. Okay. So if axis is changed, then this moment of inertia is changed, just I shown in earlier diagram. Okay. So if this axis is changed, then moment of inertia is changed. So in the next lecture we will discuss how to find out this moment of inertia for different cases. Okay.